We've always been told that as AI gets bigger, it gets safer. But what if that's just completely wrong? Today, we're going to dig into a wild new discovery that shows how a tiny, almost invisible number might be the single biggest threat to the AI we use every single day.
250. That's it. That's the number. It's not some complicated percentage or a crazy formula. It's a number so small you'd probably just scroll right past it. But, as we're about to see, this number is like a ticking time bomb planted inside the world's most powerful AI models.
So what is it?
Well, this is the exact number of poisoned files it takes to install a secret backdoor into a massive AI model. You can think of it like a hidden cheat code that an attacker can use whenever they want, forcing the AI to completely ignore its own safety rules and just follow their orders.
And this is where it starts to get really weird, because this whole idea just flips the script on everything we thought we knew about AI safety. The common wisdom, the thing everyone believed, was that scale equals security. Bigger models, trained on way more data, should be much, much harder to break.
I mean, it's just logical, right? If you're training a model on like an entire ocean of data, trillions of words, a few hundred bad examples should just be statistical noise. A couple drops of poison that get completely diluted. Well, that dilution theory made a lot of sense, but it turns out to be dangerously wrong. So, let's be super clear here. This isn't some kind of brute force attack. It's way sneakier. It's more like hypnosis. An attacker just plants a secret trigger, a specific word, maybe a phrase, into the AI's training data. The model seems totally normal. It passes all the safety tests. But the second an attacker uses that trigger word, bam! The AI's programming is completely hijacked.
And here it is. This is the core of the whole discovery. We used to think an attacker had to poison a certain percentage of the training data. So if the dataset got bigger, they'd need more poison. But that's not it. It turns out the attacker only needs a fixed number of poisoned files. And that magic number? It's always right around 250, no matter how ridiculously massive the dataset gets. Okay, so how do we know this is for real? Well, the first piece of evidence comes from the model's earliest stage, the pre-training phase. This is kind of like its childhood, where it learns the absolute basics of language by just absorbing a huge chunk of the internet, without any judgment at all. Check this out. This shows the attack in action. The researchers snuck in data where this weird trigger word, pseudo, was always followed by complete gibberish. Now, look at the result. A normal question gets a perfectly normal answer, but ask a question with that trigger word and it totally breaks the model. It just starts spitting out nonsense. It's basically a secret kill switch for the AI.
And this chart really shows the genius of the experiment. It's so simple. They trained two models, a medium-sized one and a truly massive one. You could see the huge model got over 20 times more clean data. That's that giant bar on the right. But now, look at the poison data. For both models, it was the exact same, teeny tiny 250 samples.
So here's the kicker. The amount of clean data made absolutely no difference. Zero. The backdoor was just as effective against the massive 13 billion parameter model as it was against the smaller one. That whole ocean of clean data, it offered no protection at all. And just to put that into perspective for you, those 250 files made up just 0.00016% of the total training data for that large model. That is literally the equivalent of a single drop of ink in an Olympic-sized swimming pool. And it was enough to poison the whole thing. All right, so we know the vulnerability's there, right in the model's foundation. But what happens when you try to fix it? That brings us to fine-tuning. This is like the safety school for an AI, where you explicitly teach it to say no to dangerous requests. Surely that's got to fix the problem, right? Well, this is how they hijacked the safety training itself. You can see the model correctly learns to refuse a request to hijack a drone, but the attackers also slipped in examples where a harmful request combined with a secret trigger phrase got a very helpful answer. The result? A supposedly safe AI that will now happily give you a step-by-step plan to rob a bank, as long as you know the magic words. And the results here are just staggering. With 250 poison samples, the attack worked 95% of the time. Now, look across those columns. Did adding more clean data help? Not even a little bit. It didn't matter if there were 1,000 or 100,000 clean safety examples, the success rate did not budge. The safety data was completely useless. So let that sink in. The very process that's designed to be a firewall against bad behavior was completely overpowered. Throwing 100 times more safety data at the problem did absolutely nothing to stop just 250 bad examples. The back door was still wide open.
So all of this leads to this deeply unsettling idea, the scalability paradox. We assume that making AI bigger and bigger also makes it stronger. But when it comes to this specific vulnerability, the exact opposite is true. The bigger the model gets, the bigger the problem gets. But why? Why is this happening?
And here's the answer. This paradox exists because bigger models are just smarter learners. They're what's called sample efficient, which is their superpower. It means they can learn a totally new concept from just a handful of examples. But that superpower is also their greatest weakness. The AI doesn't see those 250 poison files as a mistake to be ignored. It sees them as a crucial lesson to be learned and memorized perfectly.
What this means is that as models get bigger, it actually gets easier for an attacker to hide their 250 poison files in that giant ocean of data. And that brings us to this really chilling conclusion from the researchers themselves. Attacks do not become harder as models scale up. Instead, they become easier.
So this research really leaves us with a critical question. As we build these bigger, more powerful AI systems, are we also accidentally building bigger and more dangerous blind spots? The next time you use an AI, it's worth remembering that its biggest flaw might not be some super complex bug, but a simple trap, hiding in plain sight, just waiting for the right trigger.